Okay, welcome back everyone to the final class of conformal invariance and percolation. I remind you, if you can silence your phones and share your video, if you are willing to, that would be great. I'm going to finish the sketch of Smirnov's proof of conformal invariance and percolation today, and hopefully have a moment to just look back on the course. A couple of notes. There is a one problem final homework assignment that is posted on the web and is due a week from today. It is in fact optional, but I recommend it. It's a nice problem to just get you thinking about critical percolation. It has some of the basic proofs sketched in it. Secondly, Benji made a nice point to me after class last time, which I'll illustrate here. One of the reasons we do percolation on the triangular lattice, or one of the reasons we play the game of hex, is because hex doesn't work very well on a checkerboard. If you try to play hex on a checkerboard, here's red versus blue. Red is trying to connect these sides, blue is trying to connect these sides. Here's the end of the game. Now, who's won? Right? The problem is that when squares meet at a vertex, there's no natural way to say who gets to use that vertex to connect. So this game should probably be considered a draw. We don't want games that draw for various reasons. You might wonder, why can't you do the same thing in hex, or equivalently in side percolation on the triangular lattice? And here you see what happens if you try to. I've made a similar symmetric configuration, but because of the way this rhombus is tilted, there's actually a connection between the blue sides and not a connection between the red sides. So the increased connectivity of the triangular lattice means that at the end of the game, somebody has won. And this is related to the fact that when you form the dual hexagons, that they either meet along an edge or not at all, unlike the squares which meet at a vertex. So the underlying theorem, which motivates our choice of the percolation probability, is that the critical percolation probability is a half for side percolation on the triangular lattice, which is this. And that's what we're going to study for Smirnov's theorem. It's also true that the critical percolation is a half on the square lattice, but you have to do bond percolation. In bond percolation, you choose edges rather than vertices. And then there is, in fact, always a winner, but there's a lot of things become more difficult, and the exact value of critical bond percolation is a half, but the exact value of side percolation, which is this game, is not actually known. It's been calculated to high accuracy. It's a little bit bigger than a half, 0.59, etc. Okay, so there's some important self-duality and to this lattice, which makes it well adapted to percolation. And we'll see there's some other reason why triangles are favored in just a moment. So any questions before we proceed? Okay, so before I wrap up with this last class, I just want to say that these meetings twice a week have been the Zoom meetings I most looked forward to during COVID. And so I really appreciate your participation in this long journey, and your preservation with the whole COVID experience. I hope to see you all in person someday in the not too near future, not too far future. Okay, so here's the other reason why triangles are important. We're going to reformulate percolation in terms of conformal triangles. So a conformal triangle is like a quadrilateral. It's a Jordan domain, T, with 3 marked points on it, going around in counterclockwise order, we consider T3 to be equal to T0. In other words, we take the indices mod 3. And for any conformal triangle, there is a unique conformal isomorphism to the standard one. And the standard one we describe like this: its vertices are 1 omega and omega squared, where omega is the cube root of unity. So omega is e to the 2 pi I over 3. It's the same as the omega here. Because there's a Riemann mapping to this triangle, and then it can be arranged by a Mobius transformation to take these 3 points to these 3 points. So here, Ti is just equal to omega Ti. Now, the beautiful thing about a triangle, either a conformal one or the standard one, is it comes with a natural coordinate system on it. 3 real coordinates. They're called barocentric coordinates. And these will play a crucial role in the analysis of percolation. So barocentric coordinates look like this. You want to describe any point in the interior of the triangle as a sort of weighted sum of the 3 vertices. And so the barocentric coordinates are 3 maps from, I'll give you them in the case of T naught first, to 0, 1, and they have the property that they sum up to 1. They give the relative weights you have to put on these points to describe a given point Z inside of T naught. So, in a convex set, every point is a linear combination of the extreme points. For a triangle, that convex linear combination is unique, subject to this constraint. So there's a unique way to write Z as B0 plus B1 omega plus B2 omega squared. And so what do these coordinates look like? For example, the weight attached to this point here, which is B0, B0 is just this map. It's projection to the real axis. So if you want to describe the point 1, you set B0 equal to 1 and these other 2 weights equal to 0. And along this edge, you just want to take linear combinations of omega and omega squared. So B0 is 0. So B0 is just some simple linear function of the real coordinate in this picture. And similarly for B1 and B2. So you'll notice that since B1 is a projection, it is the real part of a holomorphic function. So sorry, B0 is obviously harmonic. So these BIs are harmonic functions. Now, what happens with a conformal triangle? Well, since the uniformizing map to T0 is unique, you can pull these functions back to get equivalent harmonic functions canonically defined on any conformal triangle. So I'm drawing the level sets of B0 in this conformal triangle. And they're just defined by taking these barocentric coordinates and pulling them back. But since they are conformal invariants, you might think there's a way to define them just using conformal geometry. And there is. So let me state a theorem to that effect. So the barocentric coordinates on T are characterized among reasonably smooth functions, say C1 functions, Bi from T to 0, 1, by the following properties. First, this property I'll explain in a moment. Omega times the d bar derivative of bi is the d bar derivative of bi plus 1. And 2, there's some boundary value conditions, which are that bi of ti should be equal to 1, and bi equals 0 on side I. So when we have these marked vertices, the opposite edge from T0 is this edge here in the boundary of the triangle, and I call that side 0. So this is side 0, this is side 1, and this is side 2. So we saw that already here. B0 is 1 at this point, it's 0 along this edge. Now notice I didn't give the complete set of boundary values. And I also didn't say that these functions are harmonic. So it's kind of interesting that these weaker conditions serve to characterize barocentric coordinates, and they force the BIs to be harmonic. And there's a neat reason for that. But let me explain what this condition means. So let me remind you what d bar of any function is. D bar of f is 1/2 df dx plus I df dy. So in a certain sense, it's 1/2 the gradient of f. If we think of the gradient of f, which is a vector in the complex plane, as being recorded by a complex number with real part df dx and imaginary part df dy. And what this condition is saying is the following. Let's go over to T0. So when we're in the interior of T0, we have 3 barocentric coordinates. And what do their gradients look like? Well, the gradient of T1 increases as you move towards the first vertex. So this is what the gradient of B0 looks like. The gradient of B1 similarly points towards the first vertex omega to the 1, and the gradient of B2 points to the second vertex. And they have the same absolute value. They're the same vector up to rotation. Okay, so there's these 3 gradient vectors, and they're related in this very simple way in the tangent space. And since the mapping F is differentiable, when you pull those functions back here, they don't necessarily point towards the vertices, but they still have the property that their gradients at any one point in 3 different and equal directions, with equal magnitude in 3 directions that differ by 120 degrees. And that's what this condition says. So let me prove this theorem. It's very neat when you write it in terms of d bar. Because, for example, what can we say about the d bar derivative of B0 plus B1 plus B2? Well, if we use this relation, we find that this is the d bar derivative of B0, that's the first term. And then we have to take the d bar derivative of B1, but that's just omega times the derivative of B0. And similarly, the last term, it's omega squared times the derivative of B0. Okay, now what is 1 plus omega squared?
0.
It's 0, right? These are these 3 vectors pointing in these 3 different directions. They add up to 0. So this is 0. That means this function is holomorphic. Now I claim that this function is in fact constant. Why is it constant?
It's constant on the boundary.
That is true. There's another simple reason it's constant. Somebody else? What kind of function is this? Take a look at how these functions map.
It's bounded.
True, but it's bounded only on a triangle, so that's not enough to conclude it's constant.
It's real.
It's real. Who said that? Raise your hand. Congratulations. Yes, it's real. So a real valued holomorphic function must be constant by the open mapping theorem. So this is forced to be constant just by this simple C1 condition. That's a really beautiful and not quite obvious fact. And then when you couple that with the boundary conditions imply that at every vertex, the three numbers sum to 1. And so this constant must be 1. So that verifies that these coordinates satisfy this property. They sum up to 1. Hey, let's try that again. So let's try f of z is b0 plus omega b1 plus omega b2, omega squared b2. If we take d bar of this function, by the same kind of calculation, we get d bar of b0 times 1 plus omega squared plus omega. And that's 0. So this function is also analytic. And now something really neat happens. If you look at this function, say along this edge here, well, alongside 0, b0 is equal to 0. So this function is just a linear combination of b1 and b2. So it's just a linear combination. It's a convex combination of omega and omega squared. That means f, which is holomorphic, sends this red edge here into this edge of T0. And moreover, it does it in such a way that this point goes here and this point goes here because of this condition. So it sends this edge to this edge, it sends this edge to this edge, and so on, and it's analytic. Well, by the argument principle, when you go once around the boundary of T, you go once around the boundary of T0. So that means that F in the interior of T hits every point that's in the interior of T0, and it hits it exactly once. So this function F turns out to be identical to this function F. It is exactly the Riemann mapping to the standard equilateral triangle. And so from those two properties, it's very easy to see that these, in fact, are barocentric coordinates. So we've done something kind of interesting and a little bit different than our previous arguments. We've used, instead of trying to prove something's harmonic directly, we only studied first order differential properties. And then we use that to prove that these functions can be derived from certain holomorphic functions. They're linear combinations of the real parts of this holomorphic function and this one. And therefore, at the end of the day, they are harmonic. And that's a big theme in Smirnov's proof. Okay, so now I can give a more precise statement of Smirnov's theorem. And this characterization will be part of the proof. But his theorem can now be phrased in the following rather nice way. So let T be a conformal triangle. PH, as usual, will be T intersect rescaled triangular lattice. And I'm going to define a function, BI of H of Z is the probability of a critical percolation cluster separates the point Z from side I of our triangle. So in my picture over here, I take my triangle and I approximate it by a lattice. I pick a point Z, and then I choose sites at random in my lattice, and I might get a cluster S0, which goes like this. If I do, it separates the point Z from side 0. And so then that counts towards this probability. So this can be defined, but it requires that I discretize T so that I can do percolation on it. And then the theorem is that BI of H of Z tends to the barocentric coordinate BI of Z uniformly on T. Now, of course, B of I is initially defined only at a discrete set of points, but as we've already done for harmonic functions, there's a way to make sense of that converging uniformly to a continuous function, which in the end turns out to be harmonic. Okay, and then as we saw, when you let Z go to the edge of the triangle, so first this set shows that these probabilities are conformal invariants because these barocentric coordinates are conformal invariants. So the corollary is these probabilities are conformal invariants. And then in the equilateral triangle, the value of BI of Z is just the ratio of the length of this edge to this edge. And so we also have that the crossing probabilities for quadrilaterals satisfy Cardy's formula, or the Carlson formula, the one that becomes very simple when we consider percolation in a triangle. Okay, so that's the program. The program is to take discretized percolation and prove that it converges to these barocentric coordinates that we've introduced. Okay, and one really nice feature is we only have, so to speak, one problem to work on now. We're not working on many different quadrilaterals, we're working just on a triangle. Now, what's the program of proof? Well, we know what the program of proof is from our previous experience with say, harmonic functions. So the proof in outline will depend on three things. So the first thing is we have to show that the BIH of Z have some continuous limit. That means we need to show that when Z moves a little bit, these probabilities don't change very much. And that was really the key point in the proof for harmonic functions, was getting this modulus of continuity by a tricky random walk argument. Here we don't have any random walks to help us. The second step is to show the limits satisfy some discretized version, of, let me call the limit B sub I of d bar B sub I times omega is d bar Vi plus 1. And this will be the key to the proof. This was Smirnov's big breakthrough, was showing that there's sort of these triple Cauchy-Riemann equations are satisfied. And then the last step, which is easy, is to show that the boundary conditions are right. And then from the theorem we just proved, this will imply that BI equals standard barocentric coordinates. Okay, so let's jump in to the proof of the first statement. The proof of this statement is where the game of hex really comes to the fore. So one is really closely related to hex. And it gives you an idea of the state of the art of this theory before Smirnov proved these theorems. So I'm going to state a theorem that's due to what's now called RSW theory, or Russo-Seymour-Welsh. This is the kind of thing, this took about 20 years to develop, and it's the kind of thing people could prove before they were able to get these remarkable conformal invariants and exact values. So this is some sort of approximate statement about percolation, and what this says is the following. So let's just let Q be an ordinary rectangle. Forget about conformal invariants, just a good old rectangle like this. Then you can do percolation on the lattice approximations to this and see what the crossing probabilities are. And the strongest theorem that was known, there are some specific bounds here, but I won't say what they are, was that as you make the lattice finer and finer, the crossing probability might oscillate, but it doesn't accumulate at 0 and it doesn't accumulate at 1. Now, where it does accumulate depends on the modulus of this quadrilateral. The longer the quadrilateral is, the more this might get close to 0 or 1. And secondly, similarly, if we take an annulus, a standard annulus, then we also have a crossing probability. When we discretize, we look if there's a percolation cluster going between the two boundary components. And again, 0 is less than a lim m of the crossing probability for this annulus is less than the lim sup, is strictly less than 1. Okay. So where did these kinds of things come from? These kind of at least crude approximations to what we want to prove. So the idea of all of these things is some kind of bootstrapping. And you prove a small statement, and then you use it to prove bigger statements. So the first statement that was proved, and this one is easy, but this is where the game of hex comes in. So remember, we're doing percolation at probability 1/2. And I'm going to be working on these are actually fairly robust statements. They work for many lattices, but I'm going to be working on the triangular lattice. And instead of doing a rectangle, I'm going to do something, just for simplicity, I'm going to do something a little bit simpler, which will imply what's true for rectangles, which is I'm going to take a rhombus, not a rhombus, a parallelogram with vertices in the z omega lattice. So it's going to have height. This vertex will be at b omega. This vertex will be at a. Vertex will be at a plus b omega, and a and b are going to be positive integers. Okay, so this is just some particular graph, particular subgraph of the triangular lattice. And the first theorem, let me call this L of AB. And the first theorem is that the crossing probability for L of AA is equal to 1/2. So if I make this a perfect rhombus, then the crossing probability is 1/2. And the proof of that is easy, because the probability of a crossing in the sites that are colored going this way is exactly the same as the probability of the sites that are not chosen having a crossing going this way. But since the rhombus is symmetric, that means that the probability of a blue crossing is the same as the probability of no blue crossing. And so since the sum of those two events is 1, they must each be a half. Okay, so this is where the symmetry of the game of hex on a rhombus comes in. And now comes the hard step. The hardest step in the proof was to show, and let me see. So this is, unfortunately, it's a little bit hard to draw the way I've chosen to draw things, but we make the B sides bigger. And remember, we're looking at the probability that there's a crossing between the A sides. And so let's consider the case where the B side is now longer than the A side. So we look at, say, L of A to A. Now, it's obvious that the probability of a crossing going this way is going down as you move from the shape of the rhombus. It's harder for there to be a crossing in this larger thing. So this probability started out as a half as it's decreasing. And the claim is that this is greater than or equal to some constant greater than 0 for all A. That was the big breakthrough. And by the way, you don't have to prove it for 2. You can prove it for any lambda greater than 1 here. The big breakthrough is just showing that if you make it a little bit bigger, that as long as you're doing critical percolation, the probability remains positive, independent of this constant A. So in other words, if we take this parallelogram and we discretize it, let H go to infinity, that the limiting crossing probability can't tend to 0. And I won't give the details of the proof, but I'll say it involves something like taking this thing and cutting it into several different squares where we can apply this theorem, and then also applying a reflection argument. So it's a little bit subtle. But the main thing I want to emphasize is that once you've done this, the problem is solved. And that's kind of amazing. So that's what RSW theory is about, is once you've solved just for one oblong parallelogram, once you've proved that for one oblong parallelogram, you have a definite probability of crossing, it follows for all oblong parallelograms. And so 3 is now, it's true by induction that the probability of A, Ka is greater than or equal to some Qk greater than 0 for all integers K. And let me explain roughly why this is true. So what you do, let's suppose that this is 3A omega, and this is A here. What you do is really neat. So you cut this region into 3 rhombuses. So we have a rhombus here, a rhombus here, and a rhombus here. And now we put 2 of the rhombuses together like this. And that's one of these 1×2 rhombuses. So let me call that L1. And then we put the other 2 rhombuses together, the top 2 rhombuses together. And we call that L2. And then they overlap in this rhombus in the middle. So let me call these R1, R2, and R3. So the rhombus in the middle is R2. Okay, now don't blink. There's a definite probability that there's a crossing of L1. So P of L1 is greater than or equal to some constant Q. That's this theorem here. And there's a definite probability that there's a crossing of L2. L2 is isomorphic to L1. But look, these crossings might not link up. They don't give us a crossing from the bottom to the top. What should we do? Well, let's look at this intermediate rhombus R2. If we only had a crossing going between its horizontal sides, like this, that would necessarily join these two crossings, and then we'd have a crossing from the bottom to the top. So the probability of a crossing of R2 in the horizontal direction, I'll put a star there to indicate that I've flipped which crossing I've considered, is also something we know because that's a symmetric region, its probability is half. Okay, and now all we want to know is what's the probability that all three events occur? And the answer is the probability of L1, L2, R2 star is greater than or equal to the product of the probabilities. 1/2 Q times Q. So 1/2 Q squared. And we're done. Beautiful. But why did we know we could bound the probabilities below by their product? Well, there's one case in probability theory where we know that PAB is equal to PA times PB. When can we use this equation? Anybody?
Independence.
Yeah, that's right. That's what independence is for. The probability of two independents happening is just the probability product of the probabilities of each. So if these events were independent, then we would have this theorem. Now, are these events independent? Not in the slightest. You see, this crossing probability depends on what the sites are doing in R2. This one depends on what's happening in R2, and this one also depends on what's happening in R2. All three of them are dependent. However, there's a beautiful fact. These crossing properties have the property that the more sites that are chosen to be part of the cluster, the higher the probability gets. That is, if we take a site and we decide to add it to the cluster, all three of these probabilities go up. They are what are called monotone events. The more sites you choose to join to your percolation set, the higher these probabilities get, the more likely they are to become true. So these are what are called monotone events. And there's a very general theorem, which has nothing to do with lattices. It has to do really with logic, that says increasing or monotone increasing events are positively correlated. They're not necessarily independent, but in fact, when R2 is true, it makes it more likely that R1 is true. Because when R2 is true, more sites are turned on than what there might otherwise be. So for monotone increasing events, the probability of both happening is greater than or equal to the probability of each one individually happening. And that's why we're able to pretend these are monotone, these are independent, to get a lower bound. Okay, so that shows that once we've proved this for 2, we can prove it for 3, and then we keep going, and we can prove it for arbitrarily large regions of this type. And then we can use that easily if you really want to do square rectangles. You cover them with some sort of parallelograms or approximate them by parallelograms, and you easily get this theorem as well. Similarly, how does the annulus theorem work? That's continued bootstrapping. So now we know that there's lots of crossings in the case of rectangles. What about an annulus? Well, if you have an annulus, first you can just construct a parallelogram that crosses the annulus. And now if there's a crossing of this parallelogram, then there's a crossing of the annulus. So that makes it obvious that this limiting crossing probability can't go to 0. But why can't it go to 1? That's actually the interesting thing. Why is there always a definite chance that you can't cross the annulus? So not being able to cross the annulus is the same as there being in the complementary set of vertices a loop that goes like this. This is among the vertices that we haven't chosen in our percolation set. And if we can show there's a loop, then there is no crossing. That will give the bound on this side. And the way we do that is, again, very simple. You just cover this loop with some parallelograms. Sorry, I'm not doing it very persuasively. You cover it. Let me draw a different picture. It's easier to draw for a very big annulus. You make a rectangle that goes like this, another one that goes like this, another one that goes like this, and another one that goes like this. And now in the complementary percolation cluster, there's a definite probability of each of these events happening. By monotonicity, they're positively correlated. And when this happens, for the region, for the points we didn't choose, you can't possibly have a path in blue that joins the inside to the outside. And this is actually the statement I want to emphasize from the RSW theory, is that in critical percolation, whenever you draw an annulus, there's a definite probability that you did not choose enough points in your percolation set to connect the inner and outer boundaries. To the contrary, there's a definite probability when you draw an annulus that there's a loop of empty sites that disconnects the inside from the outside. In fact, using that, we can prove this somewhat surprising statement, which is the following. So we have our infinite triangular lattice. We start increasing the probability. There's no infinite cluster. We hit a half, and then we go a little bit past a half. There's with probability 1, there's an infinite cluster. Now what happens right at a half? Infinite cluster or none? By Kolmogorov 0-1 law, it has to be one or the other. So the theorem is for P equals PC equals a half, there is no infinite cluster. And the proof is very simple. So let AK contained in C omega be annular regions, each approximating the set where, say, 10 to the k is less than the absolute value of Z is less than 2 times 10 to the k. So these are annuli that are getting bigger and bigger. They might look like this. This is inner radius 10 to the k, outer radius 2 times 10 to the k. And but they all have the same modulus. And so by this RSW theorem, the probability of no crossing of AK is greater than or equal to some constant Q greater than 0, independent of K. Now the sum, so the sum of the probabilities of no crossing of AK is equal to the sum of these Q's, which is equal to infinity. Now the AKs, by virtue of being disjoint, they're these disjoint regions, their crossing probabilities are independent events because they involve different vertices in the lattice. So we have some independent events, and the sum of their probabilities is infinite. Well, this is what the Borel-Cantelli lemma is for. If you have independent events and the sum of their probabilities is infinite, then with probability 1, infinitely many of them happen. So this implies there exist, almost surely, infinitely many AK with no crossing. Okay, so look, here's an annulus of enormous radius, and there's no crossing of this annulus. So suppose there's an infinite cluster. Well, this infinite cluster is blue, and if I choose K large enough, it has to have some vertices of radius less than 10 to the K. So just choose K large enough so that AK encloses a point in the infinite cluster. Well, for this cluster to be infinite, it has to be able to reach outside this annulus because there's only finitely many vertices inside of it. But that means it has to cross this annulus. So in fact, if there is an infinite cluster, almost every AK has to be crossed. There can only be finitely many exceptions that are not crossed by the percolation cluster. But with probability 1, there's infinitely many AKs with no crossing. So that's a contradiction. So there's no infinite cluster. So you might say, who wins in this game of hex we're playing on this infinite board? And the answer is, since it's an infinite board, it's a draw. But what happens is very strange. What happens is a big blue cluster develops. And then a big complementary cluster by the opponent encloses it so that it can't get out. And now you might think your opponent is winning. But in fact, there's now an even bigger blue cluster that encloses this. And if you wait long enough, you'll find another complementary cluster that encloses this. So at critical percolation, you have this beautiful property that there's infinite families of nested annuli that alternate in color, where we're coloring the sites yellow and orange, at least in this picture. Okay, so this is the picture of what happens at critical percolation. Now, amazingly, we can use this to prove the continuity of these functions BIH. And why is that? Well, remember that when we're studying percolation in our triangle, here's our triangle T1, T2, T0, and we're picking 2 points, Z and W. We want to know what is the probability that there is a blue arc that separates T0 separates Z from side 0. Now suppose Z and W are in an island. Then the blue in this island can never help separate Z and W from side 0. The only way they can be separated from side 0 is by some sort of blue path like this that lives outside of their island and which connects these 2 things together. So that means if Z and W are in an island, then whether or not Z is separated from 0 is the same as whether or not W is separated from 0. So subject to the condition that they're in an island, the probabilities, if they were always in an island, the probabilities would be the same. So in fact, we can show that when Z and W are close together, they have very high probability of being in an island, and therefore their crossing probabilities are close. So the theorem is it exists a C and an alpha such that for all C and W and T, the absolute value of BIH of Z minus BIH of W is less than or equal to C times the absolute value of C minus W to the alpha. Okay, so for the proof of this, what we do is we say we enclose Z and W in a nested set of isomorphic, by which I mean of the same modulus annuli, just like we did a moment ago. A1, A2. And how far can we do this? Well, our triangle T has some reasonable size, so we could put an annulus of size 1, and then we put an annulus of half the size, and then a quarter the size, and we finally get down to the distance between Z and W. So the number of times you can do this is given by approximately the logarithm of 1 over Z minus W. Okay, now the probability of no crossing sorry, let me put this way. The probability of a crossing in A sub I is less than or equal to some constant Q less than 1. And again, these are decreasing sequence of events. So the probability of crossings in all A sub I is less than or equal to Q to the N. But when this fails, when there is at least one AI where there's no crossing, Z and W are in an island. And then the contributions to this probability is the same. So that means that the difference, BIH of Z minus BIH of W, is less than or equal to this probability, Q to the N. Because these are the only cases where this number can change. So the event of being separated is the same for Z and W outside of the very rare event that they're not in an island. Now, what's Q to the N? This is the same as E to the log Q times minus log Z minus W. And we have two logarithms here, so we can change the base. So this is the same as ZW to the alpha, where alpha is the logarithm of 1 over Q. Okay, so that's the proof of the Helder continuity of these properties. So that was a big step in the proof of convergence of percolation, was that these probabilities converge to something. But remarkably, this step was known for many years. So this is not the fundamental contribution of Smirnov. The fundamental contribution of Smirnov was to show that these functions satisfy something like the Cauchy-Riemann equations. And what was very tricky was that they were not the ordinary Cauchy-Riemann equations. They were these sort of triangular versions of the Cauchy-Riemann equations. And that argument will use the triangular lattice in a major way, and it will not generalize to other lattices, or at least it has not been generalized, which is why we only have this one proof of percolation. Okay, so now I'm going to come to Smirnov's major proof. So the situation we want to consider is we want to consider what can we say about the derivative of B. So we want to sort of we want to form a substitute for the gradient or the derivative of each of these gadgets. Now let's think about our lattice. Our lattice looks something like this. And we want to concentrate our attention on a point Z that is in one of the triangles, not in one of the vertices. And why is that? It's because the blue arcs that we're interested in using to disconnect ourselves to disconnect Z from one of the sides, they run along the one skeleton of the lattice. And if we pick a point that was at a vertex, it wouldn't be clear to which side of this line it lies. So, but if you pick a point that's in a face, then we know which side of the blue line it's sitting on. So I want to look at a picture that looks something like this. Here is T0 is at infinity, T1, T2, this is side 0. And I want to consider a nearby point W. And I'm going to be interested in the situation where Z is not separated from side W, but W is separated from side 0. So in other words, in the complementary sites, the sites we didn't choose, there's a path from this vertex to side 0. But among the sites we did choose, there's a path that goes from side 2 to side 1, and it leaves W above. And that's when we're going to see a change in BI as we go from this in this elementary way from Z to one of its neighbors. So I'm going to label this neighbor of Z Wj, and there's an adjacent neighbor down here, which I'll call Wj plus 1, and another one called Wj plus 2. Think of these as mod 3. And then I'm going to let, I want to measure the change in BI. So I'm going to let BI of ZW be the probability that W is separated from side 0, side I, but Z is not. Exactly what I've shown here. W is on one side of the line, Z is on the other side of the line. And then one can easily check that the difference, BI of ZW, BI of Z minus BI of W, which is sort of a derivative because we're just going across adjacent sites, that this is equal to, you get a contribution from BI of ZW, and then you get minus the same contribution from DI of WZ. So if we can understand how this is, so to speak, the analog of d bar of BI, at least in the direction W, and if we can, and it's a linear combination of these two terms. So if we can understand how these two terms behave, we'll understand how this behaves. And now here's the amazing theorem, and it's an exact equality. The theorem is that DI Z Wj is equal to DI plus 1 Z Wj plus 1. Wow, so what does that mean? It means that this quantity DI Wj, which is sort of measuring the derivative of BI in this direction, is the same as the derivative not of BI, but of BI plus 1, but in this direction. So it's an exact analog of the equation omega d bar BI equals d bar BI plus 1. The omega serves to rotate the direction you're moving, which is this here, and the BI plus 1 is changing the index of which difference you're measuring. Okay, so I want to bring this down to earth just a little bit by showing you a picture. So this is on the web page. So here's an actual simulation of. This is not a simulation. I did this by hand. But here's 2 points, Z and W, and the blue sites are in the percolation cluster, the yellow sites are not. And what I've done is I've colored in light blue the triangles that are separated from side 0. And there's a key subtlety here, which is that the separation has to be by a simple curve. Can you guys see my cursor? Can you wave your hand if you see it? Okay, so here's the simple curve that separates W from side 0. And everything above this is shaded in because it's also separated from side 0. But see this point right below W, that doesn't count. Even though it's in this little loop, which could be attached to this simple curve, there is no simple curve, which goes from side 2 to side 1 and encloses this region. Because you have to come back to this site, the bottom vertex right below W. Okay, so this is the region where we are separated, and this is the region where we're not. And what you see is that what's critical here has very little to do with W. It has to do with Z. If you look at the triangle for Z, it has 3 vertices, and there's 3 critical paths emanating from this vertex. First, there's a yellow path that goes from one vertex down to side 0. That's ratifying that Z is not separated from side 0. But then there's a simple path that starts at the top vertex of Z and goes to side 2. And there's a disjoint simple path that starts at the last vertex and goes to side 1. And those ratify the fact that W, its adjacent cell, is in fact separated from side 0. So actually, this event where Z is not separated but W is, has very little to do with W. It has to do with what happens at the 3 vertices of the triangle containing Z. And what happens is there are 3 disjoint simple paths. There's one that goes to side 0, one that goes to side 1, and then one goes to side 2. So we're really just studying not so much the properties of WJ, but the properties of Z. And as I emphasized, there's 3 special paths here. There's this path, I should probably use 3 colors. There's this path, which goes to side 1. There's this path outside of the percolation set, which goes to side 0. And then there's another path inside the percolation set, which goes to side 2. So we can kind of forget about WJ for just a minute and concentrate on Z and these paths. Now, there might be many paths that go from Z to side 0. So to make our construction a little bit more canonical, what we do is we choose the path that's farthest to one side. So I'm going to take this extreme path. I'm going to try to push this blue path and this orange path as close together as possible. So there might be more than one choice for both. So let's choose them so that they're as close together as possible.
Kurt, your screen is still shared.
Sorry? Oh, thank you.
Oh.
Okay, so let's choose these 2 paths so that they're as close together as possible. And then there's a region in here where there's all sorts of orange and blue. Let's not worry about that for the moment. And then we have this path here, which is blue and goes all the way to side 2. And now we do the following amazing thing. We say, just looking at this region, let's see what happens if we reverse colors. So if we change yellow to blue within a fixed region, we don't change the probabilities of the configurations because yellow and blue are being chosen with equal probability. So the probability of this configuration happening together with this one is the same as the probability of this configuration happening together with this one with its colors reversed. So let's reverse the colors. So if we reverse the colors, then this path becomes blue, which is pretty easy to overwrite. And then this path becomes yellow. Sorry, this path starts up here. This path becomes yellow. And now what do we have? What we have is a blue path which separates WJ plus 1. And it doesn't separate it from side 0 anymore, it separates it from side 1. And on the other hand, we have this yellow path which joins Z to side 1. So in other words, for each event which contributed to what this is showing is that D0 of ZWJ, which was the event I started with, separation from side 0, is the same as D1 ZWJ plus 1. Okay, so we were able to move from WJ to WJ plus 1 at the cost of changing our separation consideration from separation from side 0 to the study of separation from side 1. And this is an exact equality of probabilities. It's a miracle. And it's a miracle that's very special to the triangular lattice. Okay, so this is the heart of Smirnov's proof. It's not bootstrapping, it's called color swapping. Okay, so how do you finish the proof? We have these functions converging uniformly to continuous functions, and we have these things that satisfy something that looks like this C1 equation. Now, if we knew the convergence were C1, we might be able to prove that something happens in the limit. But instead of doing that, what we do is we use not this fact directly, but the corollary that we used, which was we used this to prove that the integral around a circle of bi b0 h plus b1 h plus b2 h dz over a certainable path tends to 0. In other words, these equations show in a combinatorial sense that this function is holomorphic. And since it's holomorphic, its integral around a loop should be 0. And that turns out to be true, but there's a small error, but the error goes to 0 with h. And so what this shows is that this limiting function, these guys converge to b0 plus b1 plus b2. Remember, we only have uniform convergence, but integrals behave correctly under uniform convergence. So these all integrate to 0. So this integrates to 0 over loops, and that implies this function is holomorphic. And by the same token, the function b0 plus omega b1 plus omega squared b2 is holomorphic. And that's enough to prove that these must actually be barocentric coordinates at the end of the day. Okay, so the final step was to say, I'm not going to try to prove that some differential equation persists in the limit, even though I have it at a combinatorial level, but I'm going to go from the differential equation to the vanishing of certain integrals. Those behave correctly under uniform limits, and that still allows me to conclude that these linear combinations of the limiting functions are holomorphic. And that allows me to conclude at the end of the day, by the way, that the BI are harmonic. And it's kind of wild because it was realized early in the study of percolation that these BI should be harmonic, but it seems almost impossible to prove directly that they're harmonic. And the really terrific thing about Smirnov's argument is it does that by going through analytic functions rather than differential equations and harmonic functions. Okay. So there's a lot more details to be filled in, but I hope I've given you a glimpse of the main ideas in this big breakthrough relating conformal invariance to percolation. So let me just finish by stepping back and kind of jogging your memory about the main themes of this course. So the main theme of this course was conformal geometry. And the most important theorem was that if we had a simply connected region, we could find an analytic map to the unit disk. This is the Riemann mapping theorem. Now, what flowed from the Riemann mapping theorem were many interesting considerations. For example, we were able to get a natural hyperbolic metric then on any plane region we had the Schwartz lemma, and there's a sort of geometry underlying regions that are only defined up to a conformal change of coordinates. But rather than pursuing that direction, we related the theory of, we took a different tack to conformal invariance, which is we also observed that harmonic functions are conformally invariant. If you have a harmonic function on U, it's the same thing as a harmonic function on delta up to a change of coordinates. Quantities like the Dirichlet energy were conformally invariant. And this led us to the study of things like harmonic measure and capacity and the equilibrium measure. Electrical pictures of what can be defined using just the conformal geometry of a region. And then to understand harmonic functions better, we related these to random walks. Because the harmonic functions on a lattice had a very simple description. They were the ones that gave rise to martingales. Their expectation value remained constant as you performed a random walk. And here, it was easy to solve things like the Dirichlet problem. So things became sort of easy when we passed to the lattice version, but then we broke the conformal symmetry. And so that raised the interesting problem of showing that in the continuum limit, this lattice model for harmonic functions converged to the standard analytic model. And so this was an instance of using continuum limits. But then there was another route to the same discussion, which is we could also take continuum limits of random walks per se, and this gave birth to Brownian motion. And then Brownian motion could be used as a tool to feed directly into things like the solution to the Dirichlet problem. And it led to probabilistic interpretations of harmonic measure and equilibrium measure. Okay, and then what I've tried to give you a glimpse of in this last bit of the class was another instance of this theory, percolation. And the interesting thing about percolation is we didn't know what its continuum limit was going to be. But when we studied harmonic invariance, there's another direction we went into. We studied the theory of extremal length. And we became conversant in things like the modulus of a quadrilateral. These conformal invariants of regions. And then what we proved or sketched the proof of was that the crossing probabilities for percolation can be neatly expressed in terms of these standard conformal invariants. So there is an underlying process here, which we've seen two examples, one sort of standard and somewhat elementary, but not trivial, another rather deeper, which is that there's frequently objects of interest in probability theory and physics, especially in quantum field theory, that can initially only be defined in a discrete model. And then to carry out an analysis of them, what one wants to show is that these discrete models have some sort of limit when you make the discretization finer and finer, and that limit has a very rich set of symmetries, perhaps it's even conformally invariant. And that rescaling only works when you're at the critical probability, that is, when you're at the phase transition for the process. So there's some deep physical idea that physical phenomena undergoing phase transitions become scale invariant, and that's captured by conformal invariance. So I've given you a glimpse of this idea that conformal objects are important and that they arise naturally as the limit of discrete models. And if I had just a few more seconds, I would explain one more thing, which is the next element in this story from the point of view of mathematics, which is SLE. So let me just say a word about SLE. There's one problem you might not like about Brownian motion. Brownian paths cross themselves over and over. They make a big mess. How can I construct a random simple curve as opposed to a random curve in the plane that crosses itself? And this problem has been pursued from the point of view of discrete models and continuum limits for many decades fruitlessly. So people said, well, what I'll do is I'll look at all the walks that you can take on the integer lattice. Let me posit that they don't cross themselves, take that subset, and then take a continuum limit. And nobody was ever able to make that work. And the beautiful development, which was pioneered by Schramm and then developed jointly by Schramm, Lawler, and Werner, should probably be called SLW instead of SLE, was to go directly to what that continuum limit should be. They used ideas from conformal mapping to give a construction of random simple closed curves. And then much later, people proved that in fact, that those beautiful models are in fact the continuum limit of these discrete processes. Okay, so my ambition was to give a glimpse of the area of conformal geometry and some of these continuum limits. But as I say, it's only the tip of the iceberg. And I hope at least it's opened the door for you to learn more about those topics. Okay, thank you.
Thank you.
I will have office hours tomorrow, by the way. Please stop by if you never have before.
Thank you.
Yep.
Thank you very much, Professor.
Thank you, Sardar.
Thank you.
Bye.
Thank you. See you tomorrow.
Yep.
Okay, thank you for the nice class.
Okay. So I really was surprised by that thing with barocentric coordinates. And I really enjoyed it. Is it possible to canonically so like if you want to have 4 vertices or not greater than 3 vertices, it's not a canonical, there's no canonical choice, at least initially, for coordinates.
Well,
I'm wondering, is there a way to sort of canonically do that so that you can attempt to do
so
something?
in a quadrilateral, there are similar coordinates. You have 2 opposite edges, right? You take the harmonic function that's 1 on one and 0 on the other. That gives you the x coordinate. You take the harmonic function that's 1 on the bottom and 0 on the bottom and 1 on the top. That gives you the y coordinate. And then you put those together. They're not holomorphic unless you get their scale factors right, but they are analogous. But they're not, they don't have these same properties at the vertices. Yeah.
I guess what my wish is to have coordinates that are like actually like an actual weighted sum of the vertices and then sort of impose some extra condition.
Yeah. Yeah. So one thing you could do, which would be kind of interesting, is so that just imagine that you might as well assume you're in the unit disk.
Unit disk.
Yeah.
Okay.
And now imagine you have 4 points and you put tiny intervals around each of these 4 points.
4 points on the boundary?
On the boundary. Okay. You have 4 points on the boundary, you put tiny intervals around each of these points. And now, wherever you are in the disk, you can say, what's the total harmonic measure of those intervals? And what's the individual harmonic measure of the intervals? And that will give you 4 numbers that sum up to 1.
Wait, so but why would they sum up to 1? Because
the probability, the sum of these 4 harmonic measures is 1 because they're disjoint. They sum up to the, I normalize by this total sum of the 4 intervals,
Yeah.
right? So I look at the relative distance to each of these things. But the problem is, what that gives me is a map from the disk into the 3 simplex, right? It gives me 4 numbers that sum to 1. That's a 3 simplex. And obviously it's not surjective. So I'm then just left with the problem of which four tuples of weights arise.
Yeah. I don't know. I hope that my wish is that there'd be something sort of nice and simple, but I suppose that there probably is not, because otherwise people would.
Well, nobody's, even in Smirnov's own paper, he doesn't talk about barocentric coordinates. So I introduced that in this class to explain what he's doing. And I checked with the experts. They said, oh, that's a nice way of looking at it.
Oh, really?
Yes.
I guess. I don't know, I'd be incredibly happy if it was possible to prove the Schwarz-Christoffel mapping was what it was by a similar argument. It'd be very, very cute.
It would be. Yeah, that's cool.
But
That's
I really, just the
well,
argument,
this is something
the
that's,
argument for the triangle is like really.
I mean, this is something I meant to emphasize. I have a note to put it in the course notes. In the course of solving this problem, we constructed the Riemann mapping from teat to the standard equilateral triangle by a random process.
By the random process.
So I can compute these percolation probabilities,
Oh, okay.
take the limit, I take a suitable linear combination, and I get the Riemann mapping.
Yeah.
Yeah, so that would be really cool if you could do the Schwarz-Christoffel formula even by a random process.
Okay, so here's a sort of, actually, I'm also just interested if you could say anything about applications of this theorem, but also Alec may have a question.
Oh,
Hi,
I don't
Alec.
have a question. I'm just lurking.
You're just lurking. I used to be such a lurker. I have a lot of sympathy for lurkers. Or as they call them on BitTorrent, leeches. You guys know what a leech is?
The animal, it like.
No, I know you know what the animal is. Do you know, Alec?
I guess not. I mean, I know like if you like, you can leech a solution off someone for like a PSET, but I don't know if that's like.
No, so hopefully you don't know how BitTorrents work, but if you did, you would know that a BitTorrent is a way of like taking a Hollywood movie that's not supposed to be available and putting it on the internet so anyone can get it and nobody can obstruct you getting it. And what happens is everybody who has a copy, when they're logged onto the internet, this program is allowed to take little pieces of their copy and send them off to other people. And if you want to download it, you go onto the BitTorrent site and it goes and sends out signals to all these BitTorrent clients, and they all send you little pieces of the movie and assemble it, and then you get it. Okay, then what you should do as a good citizen is stay on the internet and leave that copy available for everyone else to download. But if you like immediately sign off, say, I don't want to be caught for piracy, then you're what's called a leech.
I see. Okay. I've torrented movies before, so I guess
You can tell me, I will not pass it on further. I think in the future, all people will just give up on trying to control information, and everything will be a subscription service. I mean, there should just be something that you pay, $1 a month to, and you can download all the content that's available in all the world, and it's distributed evenly to the content providers.
I don't know. I don't necessarily agree with that.
Well, this has already happened in music, right? I mean, nobody buys CDs anymore, but people use Spotify, they use Apple Music, and that's how the industry has survived.
I am curious about if there are any interesting applications of Smirnov's theorem that you know.
Oh, I didn't get to talk to you about my friend Ken Golden, who goes to the Antarctic, or did I?
Tell me about him.
Okay. So one application is if you study it hard enough, you get to go to the Antarctic. Um, let's see, applications.
I guess like, okay, like, is there like a more fundamental question that it's like trying to ask, or is it just
Well, the
Yes.
real question is
like,
in some sense, suppose somebody said, I'm trying to construct Brownian motion, I just can't do it. But there should be a probability that a Brownian path starting at this point hits this point on the boundary of a region. And then I say, I prove that's a harmonic function. And I say, hey, I've solved Brownian motion, right? But people will say, well, you should actually construct Brownian motion. You shouldn't just find this probability. And so it turns out that Smirnov's results are powerful enough to construct a process called percolation in a region, that's a conformally invariant process, just like Brownian motion is conformally invariant. It constructs random connected sets in an arbitrary region. And that's not at all obvious from what we've done so far, but it can be extracted from it.
wait, a random connected set? So this is like
So you construct this, in fact,
connected the island of the origin or something like that. Is that what you're saying?
no, it would, so you could consider, suppose you have two opposite edges. For each percolation cluster, you could take all of the continua that go between the two edges. And then you could try to take their limit. And that turns out to exist as a random subset of the region. So that's and it's conformally invariant process on the region.
How do you handle random subsets? Like it's not a random variable. I don't
Do
know.
you know what the Poisson process is?
Yes.
So, Poisson allows you to choose, say, a random subset of the integers.
Yeah.
Roughly speaking, you flip a coin with probability to get every integer and just take that set. It also allows you to choose a random set of points in the plane so that the expected number of points in any measurable set is the measure of the set. So that's already pretty interesting. That's a random process taking values in discrete sets of points. Brownian motion produces random paths for you. So, the set of compact sets,
Yeah.
do you know what the Hausdorff topology is?
A Hausdorff topology.
Yeah, so like
I don't.
if you take the square, and
Yes.
you take all the compact subsets of the square, that it turns out to be a metric space.
Do you do some inf of sup of or sup of inf of distance?
Yeah, right. You say two compact sets are close if an epsilon neighborhood of one contains the other and vice versa. Yeah? And use that to define a metric. That's called the Hausdorff metric. And it turns out the set of compact subsets of a compact set is itself compact. So, you have the set of compact subsets of the square. That's pretty good for measure theory, right?
Yes.
You could just,
So you can form a probability space on the set of compact subsets. And
yeah,
that's what you're doing with the.
exactly.
Do that as the.
You put a measure on that space.
It's not so conceptually crazy, I
It's
guess.
not crazy. It's not crazy.
Yeah,
Your observables are you take a ball and you ask what's the probability this random set intersects this ball. Those are the kind of correlations and functions you'd like to extract.
Okay, well, thank you. And I hope I read more on this because I really do like it. Anyway,
Well, the bibliography for this course, the syllabus is now like every day I add another paper to it. So there's a lot of material there if you want to go farther.
Subject to my own. whatever,
Subject to the constraints of reality.
subject to my own choice of allocating my time.
Exactly.
Thank you so much.
Good to see you, Henry. Thanks for all your questions.